Good afternoon, class. Welcome to MA 351 Linear Algebra. I hope everyone is safe and doing well. Today we're going to continue section 3.5 on change of basis. So what we've done so far is we've discussed that for vectors in Rn, if we take a basis for Rn, we can represent vectors in terms of their coordinates relative to that basis. What we've also discussed is that if you take an m by n matrix, you can represent that matrix by a linear transformation T sub a, which maps from Rn to Rm, and then you can put bases on both Rn and Rm and represent the linear transformation in terms of a matrix relative to the new basis. So in other words, you can look at how a matrix changes when you work in terms of coordinates relative to different bases. Now today we want to extend that to general vector spaces in order to express vectors as coordinate vectors relative to a basis and to represent linear transformations between general vector spaces in terms of a matrix relative to a basis. So to discuss the theory, let's let V be a vector space, and let's let B be a basis for V. Now notice here that B could be any basis for V. V has many bases. So we're quite used to the situation where we're working in Rn, in which case we have coordinates just as the entries of our vector. So those are the coordinates relative to the standard basis. But as it turns out, vector spaces don't necessarily come preloaded with a basis. That's sort of an illusion of just working with vector spaces like Rn. So then when we write down coordinates, we have to first fix a basis, and our coordinates are dictated by the basis. Now, we can write any vector y in V as a linear combination x1, b1 plus x2, b2, and so on, as a linear combination of the basis vectors with weights x1, x2, all the way through xn. Now, since B is a basis, as it turns out, the weights exist and they're unique. So then we can represent y using a unique coordinate vector, capital X, where the entries of x are just the weights x1, x2, x3, etc. So then we represent x by a vector in Rn. Now, what we'll eventually say is there's actually a linear transformation given by writing down this coordinate here. So what we're trying to say here is that when I take linear combinations of vectors like y in V, that corresponds to just adding the entries of the coordinate vector. So that's the coordinates x1, x2, x3, etc. So it corresponds to adding the entries of the coordinate vector in Rn. So vectors in V look like vectors in Rn. Additionally, note that since V has a basis with n vectors, as it turns out, any n-dimensional vector space V looks like Rn. Now, as an example, let's look at the space P2, which is defined to be the space of all polynomials a0 plus a1x plus a2x squared of degree at most 2. So we can think of P2 as the space of quadratic polynomials. And then let's equip P2 with the following basis, which I'll denote by S for standard basis. This is the basis 1x squared. So every polynomial can be written as a linear combination of the basis vectors, or the basis polynomials, where the weights are just the coefficients in the polynomial. So then it's natural to ask, what is the s coordinates of p of x equals to 3 plus 5x plus 7x squared? Okay, so I paused for a bit just in case people wanted to work through this on their own, but let's just continue. As it turns out, the coordinates of P are just the coordinate column vector 3, 5, 7. So what that means is that the coordinates here, the 3, the 5, the 7, that's just the entries of this S-coordinate matrix. So that adding quadratic polynomials looks the same as adding vectors in R3. We add the corresponding coefficients, just like we would add the corresponding entries in R3. Now, P2 has many, many other bases. For instance, consider the basis B, which is 1, x minus 1, x minus 1 squared. So then we could ask questions like, which polynomial in P2 has B coordinates 3, minus 2, 4? So that's the coordinates with respect to the basis. Right here, the basis 1, x minus 1, x minus 1 squared. All right, now I'm going to pause for 10 seconds so that you can work on the problem. And then we'll continue the video from there, and we'll see if you got the right answer. So you can pause now. Okay. Now, all right, so we want to know what polynomial P has B coordinates 3, minus 2, 4. Well, all we have to do is write down the polynomial here, where we take the entries 3, minus 2, 4, and put them as the weights on the basis vectors 1, x minus 1, x minus 1 squared. So then we get 3 minus 2 times x minus 1 plus 4 times x minus 1 squared. Note that with the 3, we secretly have 3 times 1, where 1 is the basis vector. So then from there, we can expand the polynomial and simplify, and when we do that, we get the polynomial 9 minus 10x plus 4x squared. Notice that the B coordinates of P, the 3, the minus 2, and the 4, they're very different from the coefficients 9, minus 10, 4 of P. All right, now let's consider the following other question. So now, rather than looking for a polynomial with given B coordinates, let's do the reverse and look for the B coordinates of a given polynomial q of x equal to 5 minus 6x plus 4x squared. If you'd like to work on this problem, you may pause now. Great, so let's continue. Hopefully you got the right answer. We want to find the B coordinates of q of x equals to 5 minus 6x plus 4x squared. Now, in order to do this, we have a basis with x minus 1 and x minus 1 squared, so we need to introduce x minus 1s into q of x. Well, what we can do is we'll start with the quadratic term, which is 4x squared, and we'll replace that with 4 times x minus 1 squared. But when we do that, x minus 1 squared is x squared minus 2x plus 1. So we need to offset that by, we subtracted 4 times 2x, so we have to add 8x. We added 4 times 1, which is 4, so we have to subtract 4. So then we have the 8x minus 4 as offsets at the end. So then we simplify to get 1 plus 2x plus 4 times x minus 1 squared. Now let's move to the 2x. We want to replace 2x with 2 times x minus 1. We subtract 2 times 1, so we have to add 2. Then we simplify to get 3 times 2, 3 plus 2x minus 1 plus 4x minus 1 squared. So then, in conclusion, the B coordinates of Q are 3, 2, 4. So it's just the coefficients on Q of x are the weights right here. Now, what one might try to do is from the get-go just replace the 6x with 6x minus 1 and the 4x squared with 4 times x minus 1 squared. Now, if you did that, we'd still have this offset 8x out on the end. So then we'd still have to repeat the same thing, replacing this with 8 times x minus 1. So the mechanics of the problem are, I start with the quadratic term, replace that with 4 times x minus 1 squared. Then I simplify and move on to the linear term to replace the 2x with 2 times x minus 1 squared. Now let's return to the general setting where we have a vector space V with a basis B for V. Now, before what we did is we defined a point matrix, which basically multiplying by the point matrix went from the coordinates to the point. And we also had a coordinate matrix where we went from the point to the coordinates. Now, the difference here is we want what's known as a point transformation, which maps from Rn, that's the coordinates, to the points in V. And since V is a general vector space, this point transformation is no longer represented by a matrix. It's just a linear transformation. Nonetheless, what the point transformation will do is it'll map a point x, or it'll map coordinates x to a point y in V. So we'll denote the point transformation by T upper P sub B. The P means point transformation. The B means the basis. And this is going to map from coordinates in Rn to the points in V. And so more explicitly, what the point transformation does is it takes a coordinate vector with coordinates x1, x2 all the way through xn, and it returns the linear combination x1, b1 plus x2, b2 plus xn, bn, which is the point vector y. Now, since B is a basis, it's quite clear from the description that the point transformation is a linear transformation. But moreover, since B is a basis, it's actually an invertible transformation. So for each coordinate x, there's unique point y, just by applying the transformation and taking the linear combination here. But also for each point y, we can find the x coordinates. There's a unique choice of the weights x1, x2 through xn. So any linear transformation, which is also an invertible transformation, is called an isomorphism. Again, this isomorphism, it takes coordinates in Rn and maps to the point point y in V. So when I add the coordinates, that just means I add the corresponding entries. Well, that's just adding the corresponding weights on the B sub i's here. So then additional linear combinations of coordinate vectors in Rn look the same as linear combinations of points in V. So this means that V looks like Rn. Now in particular, again, V has a basis consisting of n vectors. So if we find if V is an n-dimensional vector space, so V is n-dimensional, then we can take a basis of n vectors B, and then so every n-dimensional vector space V looks like a copy of Rn via the point transformation. Of course, it's worth noting that there's many other point transformations one could do. One very silly thing one can do is you could actually set up a transformation where you map 2x2 matrices to polynomials in P3. So that's to cubic polynomials. So how do you map a square matrix to a cubic polynomial? Well, a square matrix has 4 entries, since that vector space is 4-dimensional. But a cubic polynomial has 4 coefficients, so that's 3 plus 1 coefficients, since that space is 4-dimensional as well. So then you can just simply write down a polynomial whose coefficients are the entries of a 2x2 matrix. And this defines a isomorphism. So there's many, many isomorphisms out there, but in this course we'll be mainly interested in isomorphisms between an n-dimensional vector space V and Rn. And so that just means that V and R n look the same in terms of taking linear combinations. Now, since the point transformation is invertible, it has an inverse map, which we'll call the coordinate transformation T upper C sub B. Again, the B is for the basis, but now C is for the coordinate transformation rather than point transformation. So let's see. The point transformation mapped from Rn to V by mapping the coordinates to the point. So now the coordinate transformation does the reverse. It maps from V to Rn by mapping the point to its coordinates. All right, now what we're going to do is have our first intermission. So in order so that you don't lose focus having to listen through an hour-long lecture all in one go, what I decided to do is include some examples you can work through on the lectures, and also to include these intermissions so that one can take breaks, or if one wants, one could also go to the second part now. So if you'd like to take a break right now, you may do so when I say now, and then afterwards, please pick up with part 2 of the video, where for part 2, so part 2 is a separate video, and part 2 will cover how you compute a matrix of a linear transformation relative to a basis. So your intermission starts now.